Hello, welcome to my channel. Today we're gonna continue from the last lesson, which is about wave function. Today we're gonna talk about operators and differential equations. So let's get started. So first, let's take a look at this. We have h bar over I, the partial derivative of psi is equal to h bar k psi and equal to p psi. This is the momentum operator p hat, and if this is true, then we can call p hat an operator. And even more, if p hat psi satisfy this, which is p psi equal to p psi, this is like a number instead of like you gotta get that when you have an operator act on a function, it would give you something back, and that something could be like a number times the function itself. So when this is true, when this is satisfies, um, satisfies, this would lead to p being the eigenvalue of the function. P would be the eigenvalue, and psi would be the eigenfunction or eigenstate, as we say in quantum mechanics. And next, let's say that you have your E equal to the kinetic energy only, as we haven't considered it being in a potential yet. So this is the free energy of a particle. So we can say that E psi would equal to this times psi. And we can expand this by doing some manipulation. Well, this correctly, it would be like E hat equal to P hat squared over 2m. And when we expand this, it would be P over 2m P on psi. This we know is this. So continue expanding. It would be P over 2m h bar I d psi dx. And we can pull that out and do it again. And the final solution you would get would be minus h bar squared over 2m, the second derivative over x. So this would be equal to E psi also. So we can say that psi here is an eigenstate of the energy. So from this, we can take a look at the free Schrodinger equation. So the free Schrodinger equation basically means that your particle is not in a potential of sorts. It's free. So nothing pulling it out or like pushing it up. And it would take form like this, the time dependence, and this is the energy part. And for proof, let's try psi equal to the exponent ikx minus I omega t. You put this in, you would get something like IH bar minus I omega 2m minus ik. Is it ik squared? Yeah, it is ik squared. If we got a psi here as well, you would get from this you can get something like h bar omega would equal to h bar squared k squared over 2m. And if you expand this even more, you would get the same thing as here, which is E would be equal to p squared over 2m, as k is equal to p, and this is E. So ultimately, this is correct. And next is the general solution for the free Schrodinger equation. It would take form as this: psi of x and t would be the integral over dk of a function phi k, and the exponential part e to the ikx minus I omega t. And I think I forgot to mention this in the last lesson, which, like, you bring this from the x space to the k space, and this is called a Fourier transform, which basically means that you would want to switch the plane you're considering for the function to be like localized at some point. This is a Fourier transform. This is a very fascinating mathematical kind of transformation. It is very helpful as well. And from this, you can just get the group velocity, which is d omega over dk around k naught, and this is pm. Yep. So that's basically it for today's lesson. Goodbye.